a smooth cubic. Go. This is again smooth. So this is smooth projective. Of course, we know that if y is a surface, then we get exactly 27 lines. So in this case, it's not connected. The Fano scheme is not connected. But as soon as we deal with threefolds and above, then it's actually connected to. So it's irreducible for n strictly greater than 2. And just for reference, let me state the dimension of this thing. And it's 2n minus 4. Of course, we know much more about this Fano variety. I'll come back to this, but that's all we need for now. And the second moduli space is the Hilbert scheme of 2 points on Y. So this is always smooth projective whenever we start with a smooth projective variety. So it's the scheme parameterizing the length to closed subschemes. Of course, there are not many options for a length to closed subscheme. At either a point in the Hilbert scheme either consists of or corresponds to 2 distinct points, or sort of if these points collide, you can imagine a point and a tangent vector. So from this description, from these 2 types of points, it's quite easy to see that you can construct this Hilbert scheme explicitly as the blow-up of the product of y with itself in the diagonal. So this exceptional divisor is going to give you these tangent directions, and then of course we still have to mod out by the permutation action. And from this description you immediately see again that you get something smooth projective. And of course this guy is of dimension 2n. All right. So these are the varieties, the smooth projective varieties showing up in this relation. Where does it actually hold? So it takes place in this Grothendieck ring of varieties. So K0 bar is the Grothendieck ring of varieties. Sorry, I have this very cheap tablet, so my writing is even worse than usual. And so by definition, this is the free abelian group generated by the isomorphism classes of varieties over K. And we mod out by these so-called scissor or cut and paste relations. Scissor relations. So we say that the class of U is equal to the class of Z plus the class of Y is equal to the class of Z plus the class of U if Z is a closed subvariety of Y with open complement U. Hence the name scissor or cut and paste. And the product is just the product of varieties. So with that out of the way, we can now state this relation, which is due to Sergey and Evgeny. So it says there is a relation the class of the Hilbert scheme is equal to the class of n-dimensional projective space multiplied by the class of the cubic plus L squared times the class of the Fano variety. So this is taking place in this ring we just defined. And L is, of course, the class of the affine line. So it's the Lefschetz motive. All right, so this is the YFY relation. So we'll see in a minute where this comes from. It's a very geometric thing, but so what they do in the paper, of course, they don't, I mean, this is quite easy to prove, but they actually use this to compute the, say something about the Hodge structure on the Fano variety and to discuss rationality of cubics. I think at the time, sort of the main surprise was that if one assumed the cancellation conjecture in this growth and degree of varieties, so which says that this class L here is a non-zero divisor, and then from this relation and a few similar ones, one could deduce irrationality in a very general smooth cubic fourfold. Of course, now we know that this cancellation conjecture is not true, but still there are very interesting links to rationality, and it's very nice preprint. I encourage you to have a look at it. But so what I want to focus on now is on motivic measures. So these are just ring morphisms from this growth in the ring of variety to some other ring R. And in fact, sometimes for one of the examples, it will actually just be a group morphism, ring or group. So these are also interesting. And of course, the point is that somehow that whenever you have a relation in K0 var, you get a corresponding relation in R. And this growth in the ring of varieties, it's somehow small enough to allow many relations, but it's sufficiently universal to admit many interesting motivic measures, if you like. So this is actually something one can do a lot with. And let me try and say something about 3 examples. So first we can consider mu Chow. So this goes from our growth in degree of varieties to K0 of Chow motives, say with rational coefficients. And so here, remember, Chow motives, this is just a Q-linear idempotent complete category. It's not abelian or anything. So here, I'm really just taking the additive K0. So I'm just imposing that the class of the sum of 2 Chow motives is the sum of the corresponding classes. So if you haven't seen this kind of stuff before, it might look a bit funny. We have varieties on one side and then Chow motives, which are constructed from smooth projective varieties on the other side. But as is typical in this in these motivic kind of stories, it turns out that this growth in degree of varieties actually has an alternative presentation where the generators are smooth projective varieties and the relations, they come from blow-up squares. So this is.
Do you assume characteristic 0, Theo?
Yes, yes. I'm just everything throughout the talk. I'm just going to do characteristic 0. Yeah, because this theorem only holds in characteristic 0, right? So I'm using this alternative presentation here. So to define such a motivic measure, we only need to say what it does to smooth projective varieties and then check the blow-up relation. So if I take a smooth projective variety, of course, I send it to the class of its corresponding Chow motive. And the fact that the blow-up relation holds here goes back to the very first paper on motives by Manin in 1968, even, I think. And note here that, of course, in this presentation, the Lefschetz motive is just the difference of P1 and a point. So it does indeed get sent to the Lefschetz motive on this side. So in particular, this YFY relation gives us a relation in this K0 Chow. And so the way you should think about this is this tells us that there is an isomorphism of Chow motives up to direct summons, basically. So we can't really say anything more than that. But in this case, it's in fact a theorem of Robert-Laterweer. Oh my God, sorry. That actually this YFY relation lifts to Chow itself. So we don't have to, it doesn't hold up to direct summons, we just get a relation here, an isomorphism of Chow motives. Then similarly, what can we do? What else can we do? We can look at the Hodge realization. And here, to make it interesting, we can look at the integral Hodge realization. So let me take C here. So here I'm looking at the category of integral Hodge structures, say pure polarizable. And again, I'm just taking K0 add here, say. And again, because of Bittner's presentation, we can map a smooth projective X to its integral cohomology. So note that in this case, I guess this is not a ring morphism because of torsion, possible torsion in the cohomology, but it's still a nice group morphism. And in fact, it behaves nicely with respect to the Lefschetz, multiplying by the Lefschetz motive and projective space. This is not so hard to see. And we get a corresponding YFY relation in this K0 of Hodge structures. And so in this case, I'm not completely sure if it's been shown to lift, but it's at the very least been sort of explored by Daniel Hilbert. And I wanted to mention this because so I'm very much an amateur when it comes to cubic hypersurfaces. Even more so, pretty much everything I know about them comes from a course I took in Bonn when I was doing my first postdoc, so a course by Hilbert. And he's now sort of writing up notes for this course, and these are some very, very good notes. So if you want to just learn about these things or learn some more, I would very much recommend having a look at these notes, which are available on his website. Officially, it was a course for master students, but I distinctly remember having to be pretty well rested to actually follow along. So I think there's something for everyone actually in these notes. So I'd recommend that. And then finally, the one that is actually sort of the motivation for us, we can look at the non-commutative motivic measure. So from K0 var to a ring which is denoted PT by the authors. So here PT is the Bondal-Orlov and Lund's Grothendieck ring, many names of pre-triangulated DG categories. So this is quite a mouthful, but let me just say in words what this is. So what we do is we take the free abelian group generated by the quasi-equivalence classes of pre-triangulated DG categories with the product of pre-triangulated DG categories and with relations coming from semi-orthogonal decompositions. So this is a nice ring. So they wrote an entire paper about this, you can check out. And again, using Bittner's presentation, you can define a morphism by sending a smooth projective guide to any of the standard enhancements of its derived category of coherent sheaves. So they're all quasi-equivalent, so it doesn't, I'm just going to be a bit lazy here and just say dbco. Notice that, yeah, and of course the fact that the blow-up formula holds here is just the consequence of Orlov's blow-up formula for derived categories. And in this case, note that the Lefschetz motive, since P1 has an exceptional collection consisting of 2 points, it just gets sent to the derived category of a point. So this is sort of one manifestation of this loss of Tate twists that one sees in non-commutative geometry, if you like. In particular, if we plug in the YFY relation, then what we get is that the class of the Hilbert scheme comes equal to n+1. So this was the class of projective space, but it has an exceptional collection of length n+1 times the class of the cubic plus L squared, but L squared goes to the unit, so it just becomes the class of the Fano variety, like this. So seeing this relation, it's very tempting to conjecture that there is a semi-orthogonal decomposition which sort of underlies this, and this is exactly what we do. So, or the main application at least. So the theorem in the paper So like I said, this is joined with Pieter, Lee. Says that indeed there is such a semi-orthogonal decomposition. This n+1 copies. And moreover, I'm going to add here, so this is just because of sort of the way we set this up. We can sort of exploit a recent result by Jiang, and so we also get, in fact, an isomorphism. Of integral Chow motives. So, which looks like this. So it says that the Hilbert scheme. Make sure I get my twists right. So it's this guy twisted by -2, and then like this. So this is now integral Chow motives with integral coefficients. So these two results together sort of lift these examples I just gave you as well. So what I want to do now is explain where this theorem comes from. And really, it's just sort of putting together a couple of things that were there and maybe embellishing them a little bit. So as you'd expect, this for this theorem, there's both a geometric and a categorical component. So somehow the geometric component consists of taking this picture that Evgeny and Sergey had, which was embellished upon by Claire-Voisin, and sort of interpreting this a bit differently. And the categorical component consists in recognizing that this is very much a situation that also occurs in homological projective duality. So it's not really a homological projective duality statement, but the things that technically need to be done are very similar. So I'll try to explain how this actually, how this follows. So, but let's start with the geometry. And so I have a picture here. So this is sort of the diagram, the important diagram. And let's look at this one bit at a time. So let's start with the bottom bit here. So this is Galkin-Shinders. And so here, let's start with the Hilbert scheme of 2 points here, and this Y2. So like I said before, a point here corresponds either to a pair of distinct points on Y or a point and a tangent vector. But in either case, what we can do is, since Y lies in a projective space, we can look at the line spanned by these 2 points, or the line determined by this point and the tangent vector. And this will give me a line in the surrounding projective space. So in particular, this line, which is determined by this length 2 subscheme, it can either be in the cubic or it cannot lie in the cubic. And so by P2, we denote all of the points in the Hilbert scheme, so all of the length 2 subschemes, such that the line determined by this length 2 subscheme, so that's my notation here, such that this line actually lies in our cubic Y. That's a closed subscheme here. That's this P2. And of course, now I can map down to the Fano variety of lines by just mapping this point to this line considered as a point of the Fano scheme. And if you look at the fiber over a point in the Fano scheme, then we see that what lies above it is just the choice of 2 points on this P1, on this chosen line. So this is actually P2, and it turns out this is indeed P2 bundle. All right, so that's sort of this left side of the picture. We have this nice correspondence. All 3 varieties are smooth projective, and this P2 is a P2 bundle over the Fano variety of lines. Then on the right-hand side, we again have a correspondence. And so here we start with Py, which by definition, is just the projectivized tangent bundle of the surrounding projective space, which we restrict to Y. So this is a projective bundle over Y, so it's again smooth. And the easiest way to see all of this is to think of the points in here, if you like, as consisting of tuples L, Y, where Y is a point on the cubic, and L is a line in the surrounding projective space containing this point Y. So that's just some easier way to think of this. So again, we see that we can very naturally define a closed subscheme by just considering only those tuples such that this line L actually lies in the cubic. So again, P is going to denote, is going to consist of a closed subscheme consisting of all those tuples YL, such that this line L is actually inside of the cubic. Okay. And again, of course, we can project down to the Fano variety by just projecting such a tuple Ly to the corresponding point, the point corresponding to L. And of course, this really is just the universal family for the Fano scheme. And in this case, since we only have a single point, this is a P1 bundle. Right. Okay, so that's already quite nice, but it turns out there's more because there's this map phi here. So this is a birational map, and what it does is the following. So if we take a length 2 subscheme of Y here, then as long as we take it in the open complement of this P2, then we know that the line it spans doesn't lie in the cubic, and so in particular it has to intersect the cubic in a length 3 subscheme. So since we already have Z itself as a length 2 subscheme, the residual intersection is just a single point. So what we can do is we can map Z, so in this open complement, to the line determined by Z and X, where so X is determined by the fact that if we intersect LZ with Y, we get Z plus X, like this. And of course, we land in the open complement of this Py, and we can also go back if we take a point in Py, not in P, then by intersecting it with the cubic, we get a length 2 subscheme, and we send it to that corresponding length 2 subscheme. So what this actually does is it defines an isomorphism of these open complements. And so you can see that if you use the cut and paste relation, and you use the fact that the projective bundle formula in this growth-unique ring of varieties, then from this lower half, you immediately recover this Y-F-Y relation in the growth-unique ring of varieties. So that's this lower side of the picture is enough here. All right, but it turns out there's actually more to the picture. Namely, there's this upper half. And so this upper half is, as far as I know, due to Claire Voisin. She was studying decomposition of the diagonal for smooth cubics. So what she proved is, or one of the things she proved, of course, only one, is that this map here, this phi, is actually desingularized by the blowup of this Hilbert scheme in P2. So this P is the blowup of the Hilbert scheme in P2. And so in particular, it also comes with the map tau prime to Py. And in fact, it's not just this desingularization. In fact, it also identifies with the blowup of Py in P. So we can blow up the Hilbert scheme in P2, blow up this projectivized tangent bundle in P, and we get the same variety B back here. That's what she showed. And under this isomorphism, also the exceptional divisors actually get identified. So this E here is the exceptional divisor, and so we get two blow-up diagrams, one here and one here. And maybe I should add that this exceptional divisor isn't also, in fact, it's the fiber product of this P2 with B. All right, so this is much more info, and here we can sort of start to see how it works. So since we now have two blow-up squares, Orlov's blow-up formula also gives us two semi-orthogonal decompositions. So if we look at the semi-orthogonal decomposition coming from this left-hand square here, then we get, so we decompose the derived category of B in terms of the Hilbert scheme and in terms of one copy of this P2. But this P2 itself is a projective bundle over the Fano variety. So this decomposes into, the end result is we get the Hilbert scheme and some copies of the Fano variety. On the other side, if we do the blow-up formula, then we get a decomposition of B in terms of Py and P. Py was a projective bundle over Y, so this reduces to several copies of our cubic surface. And P is again a projective bundle over Fy, so we get copies of Fy. So this already explains that, at least if you ignore, if you look in this growth and degraying of pre-triangulated TG categories, for example, you already see this relation come up again without using motivic measures. The difficulty in actually making this, turning this into a semi-orthogonal decomposition is, of course, well, it's just, we have one big triangulated category, this derived category of the blow-up here. We have two different semi-orthogonal decompositions. And so what we want to do is we want to sort of mutate these components around in such a way that we get the same components on one side, so we can actually cut down to get a semi-orthogonal decomposition of this Y2, which is what we're after. And in general, even if you have a diagram like this, this is difficult, if at all possible, but there's actually sort of more still to the geometry that helps us here, and it also I hope shows the link with homological projective duality. So to show this, let me start by defining this OAB here as, so these will be line bundles on this fiber product on the exceptional divisor. So I can look at the pullback of a relative line bundle O pi I. I can tensor that with pullback via pi prime of an O pi prime B. So these are line bundles on E. And then I can define the following triangulated subcategories of B, of the derived category of B. So I take my Fano variety, I pull it back to P, I pull it back further to E, then I tensor with such a line bundle OAB, and then I push it forward along the embedding of the exceptional divisor. So this is one of these AABs. And so of course, since the diagram commutes, I could have also written this as P prime pull, Pi prime pull of DBF, tensor with OAB. Sorry, OAB. And what's the point of doing this? Well, if we now furthermore assume, and I'll talk about this in a minute, talk about this more in a minute, that the normal bundle of this exceptional divisor is of the form, also of this form, so OD1, D2, say. Then if you write down this Orlov blow-up formula and the projective bundle formulas carefully, so you write down these SODs for B carefully, then what you see is that the orthogonals, the left orthogonals, so the left orthogonal of this component coming from the Hilbert scheme, which is given by pulling back via tau, and the left orthogonal of Py, which is given by pulling back via tau prime. These orthogonals actually, they're semi-orthogonal components, and that are naturally, they all consist of these AABs. So these orthogonals have SODs with components such AABs. And note that so these AABs, they're somehow we get the same copy of this Fano variety of lines up to twisting by such a line bundle. So we don't just have one big triangulated category with two triangulated categories sitting inside them that we want to cut down an SOD. We also know that their complements sort of all consist of categories of the same type, and they only differ up to by twisting. They differ up to twisting by a line bundle. And this is a situation that's actually very familiar from homological projective duality. So let me just say in words what happens there. So typically you start with some projective variety X, which has a Lefschetz decomposition, say. And then the role of this ambient, big ambient category that B is playing here is the universal hyperplane section. So the role of B there will be played by the universal hyperplane section. And the derived category of this universal hyperplane section then has two natural semi-orthogonal decompositions. One which is coming from the Lefschetz decomposition on your original variety, and where one can also find the homological projective dual as a component. And then the other one, which comes from the dual projective space, from the exceptional collection on a dual projective space. And typically what we want to do in HPD is that we want to start with some variety X, and then which has this Lefschetz decomposition, and then maybe construct an SOD for its homological projective dual. So what this boils down to is to actually take these two SODs for this universal hyperplane section and try to cut them down to smaller pieces. And this is exactly what we're sort of doing here. And also in HPD, what you see is that sort of the differences between these interesting components, they're all of the same type. So they're a bit more complicated than here, but still they basically are of this type. And so to say this a bit more clearly, and this is probably a picture that people will recognize, there's this sort of HPD method, which was, of course, goes back to Kuznetsov, but which was, I guess, made clear to many people, or clearer to many people, by Richard Thomas, and also by work of Jiang, Konelung, and G, where they sort of refer to this as playing the chess game. So what you do is you have these two semi-orthogonal decompositions, and their complements consist of all these components A, A, B. So you think of these as living on a two-dimensional grid. So one of these squares corresponds to one copy of AAB. And then your job to actually cut down the semi-orthogonal decomposition is to play the chess game. So what does this mean? Well, I'm going to try to say as much as possible without actually going to the completely technical details, but the point is that one of these SODs is going to correspond to a certain region of AABs in this chessboard. Your other SOD is going to correspond to some other region, and essentially what you do is you try to prove vanishing results between different such components, which allow you to more easier mutate these AABs past each other until you can you get an overlapping region, which then allows you to cut down the semi-orthogonal decomposition. And this is referred to as playing the chess game. So in this setting that we're in, what does this boil down to? Well, essentially what you do is you use bolt vanishing. You use bolt vanishing to prove that certain of these AABs are actually orthogonal to each other. 0 for certain values of AB, A prime and B prime. And then since you'll see that there are many of these orthogonal components, and this then makes it easier, if you like, to mutate copies past each other. And cut down the SOD. So this is a bit, I hope this is not too vague. So it's a bit more complicated. So I can't really say too much more, I think, but so this is generally the idea. You think of these guys living on this chessboard, you want to mutate a bunch of these things past each other. This is essentially a combinatorial exercise, which sometimes is solvable. So sometimes you can win the chess game, sometimes you can't, but in favorable situations you can, and somehow all computations reduce to playing around with these AABs. That's exactly the same idea as what you do in homological projective duality. But there's one thing which is important here, which I want to mention now. So I assumed here that this normal bundle of the exceptional divisor is again an OD1D2. And in fact, it turns out that to win the game, say, so these configurations of these AABs sort of have to be as simple as possible. And so what we want is we wanted this OEE. It should be as simple as possible somehow. It should be as simple as possible. And it turns out that in this situation of cubic hypersurfaces that we're considering, it's again in this notation I used before. So it's an O minus one. Which sort of comes from determining the normal bundles of these closed subschemes. So really what you have to do is determine the normal bundles of these closed subschemes here. And this is really what sort of makes this version of the chess game solvable and allows you to cut down the semi-orthogonal decomposition. But then once you have this, you could sort of step back and look at what we really needed to obtain this SOD. And so really, you don't need any of the specific geometry of this diagram. What you turn out to need is you need two blow-up diagrams, as we have here. So every variety here is smooth projective, two blow-up diagrams, two projective bundles. You want that this exceptional divisor is this fiber product, and you want these normal bundles of P2 and P to be of degree -1 along these fibers of pi and pi prime. And this actually, in that case, you're able to solve the chess game and get an SOD of say, this variety in terms of the other components in the diagram. But this is a situation that's very familiar to birational geometers. This is exactly what's called a standard flip diagram. So typically, in the easiest case, what you would have is that, maybe do in green, I hope this is not too confusing. The easiest case of a standard flip would be where the base is just a point and where we have, say, some projective space, which is embedded into a smooth projective variety with a normal bundle, which is just consists of some copies of O-1. In that case, we know we can flip the projective space and we get a diagram like this. And in that setting, it's a very old result by Bondal and Orlov that actually pulling back along, say, tau prime, so depends a bit, the order depends a bit, but pulling back and pushing forward actually gives a fully faithful functor. So this is already good. So essentially what we do is, well, first of all, one needs a family version, not over a point, but over some smooth projective scheme. This is just standard. There's nothing new here at all. But then what one really needs is one needs to sort of complete this fully faithful functor, this Bondal-Orlov fully faithful functor for standard flips into an SOD. And this is really the main thing we do in the paper that sort of all the rest follows from. So the main theorem really is an SOD for standard flip diagrams. Ooh, standard flip diagrams, where a standard flip diagram is basically what I said before. We have this diagram with these blow-ups, projective bundles, and normal bundles, which are degree -1 in the fibers. Right, and then, like I said before, combining this theorem with this lemma that in the case of cubics, we actually can compute these normal bundles, we immediately get this YFY, this lift of this YFY relation to an SOD. And this isomorphism of integral Chow motives is now follows very cheaply because so this isomorphism in Chow follows immediately because someone else did the work. So by a result of Jiang, where, sorry, let me rewrite his name. Because what he does is he considers exactly standard flip diagrams and then shows isomorphisms of Chow motives. So as soon as you know that this diagram for cubics is a standard flip diagram, you get the corresponding result on Chow motives. And at this point, I should also mention that after we put our preprint online, Jiang actually emailed us explaining that so himself and Conan Lung and G have actually sort of managed to axiomatize this favorable situation of the chess game to such a level that you can actually get both HPD and this theorem here for flips. You can get both of these from the same axiomatic setting that you just have to plug your ingredients into. So there is actually sort of a meta theorem, if you like, by Jiang, Conan Lung, and G that sort of really generalizes both this result and HPD. So it's essentially an abstract result, if you like. All right, so that's what I wanted to say here. I guess maybe, so we do, one more thing we do, which is maybe interesting to just remark, as a quick remark, is that so it's very well known that this Fy it's of general type for a cubic threefold, so for n equals 3. It's hyperkähler for n equals 4, and then it becomes Fano. But we didn't find any results on this Hilbert scheme, and so what we showed is that as soon as n is at least 3, then this is always Fano. So this Hilbert scheme of 2 points on a smooth cubic is always Fano. And so in particular, what you get as sort of a funny little side result is that you get embeddings of a hyperkähler and its general type variety into derived category of a Fano variety. So this sort of relates to this Fano visitor problem that people like to talk about. But this is sort of a side remark. That's pretty much everything I want to say about this this theorem. So I have some time left. So let me finish by.
Can I ask before you go on?
Yes.
I mean, can you say a little bit more what you mean by standard flip diagrams?
I really mean that we have a diagram like this. So we have smooth projective varieties, the normal bundle of, say, P2, the normal bundle of P2 in Y2. So if these were arbitrary smooth projective varieties restricted to a fiber, is some copies of, sorry, I really can't. Some copies of O-1. Same thing happens here. And we get projective bundles. The codimension doesn't matter, so the chess game becomes more important, but that's essentially it. So from a birational geometry standpoint, I guess one would start off with say this left side, and with this given normal bundle, and then you would blow it up, use the Fujiki-Nakano criterion or whatever to be able to contract it along the other side, and then you would get a diagram like this. But I sort of wanted to say it like this because one doesn't really need to invoke too much birational geometry. The point is really that you have these two blow-up diagrams, these two projective bundles, and the normal bundles of the closed subschemes are of degree -1 along the fibers. That's really all you need to get an SOD for, say, this left side in terms of other components in this diagram.
Sorry, can I ask about this? So in particular, the two projective bundles are Zariski locally trivial, correct?
Mm-hmm. What do you?
Like they're
These are just these, yeah, so they're really just projective bundles, projectivization of some vector bundle.
Right, yeah.
This with projective variety, yeah, for sure.
Thanks.
Yeah. Right. Yeah, I'm sorry, I hope it's clear enough. I thought it was sort of, via this example, it would be the clearest way to explain this, but yeah, so some of the main points are two blow-up diagrams, two projective bundles, and the normal bundles are of degree -1 along the fiber. All right, so let me sort of finish by talking about some loose ends, because this is somehow, in a way, this should only be the start. So this is all we do in the paper, but there's more one can guess. So of course, the Hilbert scheme, especially the Hilbert scheme of 2 points, is very well studied because it's always a smooth projective variety and has a simple description. And if you use this description, so as a blow-up mod out by this finite group action, then there's actually another result. So let me write this as a theorem. There's another result. So this is a theorem of Andreas Krug, David Blok, and Pavel Sosna. And this says that for any smooth projective variety, y, say, of dimension at least 2, there is an SOD which looks as follows. So again, we take the Hilbert scheme. And now one component is the equivariant derived category. So the equivariant derived category of the product with respect to this this permutation action. And again, we get copies of dby. So remember that in our SOD there were n+1 copies, and here there are n-2 copies. And so this really comes from this description as sort of a resolution of this of a quotient singularity, if you like. And so in particular, if you now compare summons, or say do the computation in this growth and decreasing of pre-triangulated DG categories, then you see, and you cancel the summons, then you see that the class of this equivariant derived category is equal to the class of the Fano variety plus 3 copies of the class of the cubic. So of course, it's very tempting to conjecture that there is a semi-orthogonal decomposition that explains this relation. But so far, we haven't found it yet. So it's, of course, what one wants to do is take the one we have, compare it to this one, and cut it down further. It should definitely be doable, but these copies of dby here, they're somehow embedded quite differently. So yeah, I mean, we haven't done it at all, but I think it seems like it's doable. But then there's something which is even nicer and which lies deeper, namely because if y is again a smooth cubic, like before, well, I guess, yeah, it's a smooth cubic everywhere. So we know that since it's a hypersurface, there's actually several line bundles, exceptional line bundles from the ambient projective space that survive when you restrict to y. And so we have this Kuznetsov component here, an SOD with one component, the Kuznetsov component, and then a bunch of line bundles. One. And so since this dby has an SOD like this should mean that by taking the symmetric square, if you like, of this dby. This should mean that the class of this equivariant guy actually can be decomposed in terms of the symmetric square of this Kuznetsov component. Then n plus 1, no, n minus 1, n plus 1, yeah, n minus 1 copies of ay, which sort of come from tensoring this ay with each of these exceptional objects. So you should get n minus 1 copies of ay. And then if I hopefully counted correctly, you should get n squared plus n minus 2 divided by 2 exceptional objects. So say the derived category point. So this combining this relation with the one here, you again, can cut this down further, and I particularly want to highlight the case n equals 4, so cubic 4-folds. So in that case, you see that we get 3 Kuznetsov components, which cancel out the 3 coming from dy here, and we also get 4 squared plus 4 minus 2 is 18 divided by 2, 9 exceptional objects, which cancel out these 9 exceptional objects from y here. So what you deduce is that the class of this sim2ay should be equal to the class of the Fano variety of lines. And again, one hopes that there is actually, that these categories are in fact equivalent, and this seems to sort of be the deepest statement. And of course, I would like to know if this is true or not, but I don't know at this point. So that's everything. Thank you for your attention.
Okay, thank you. Are there more questions?
Maybe on this statement that the Hilbert square of y is Fano, is this easy to prove, or is this proven anywhere? Because I guess it's clear if you look at it as the blow-up of the symmetric product, then the canonical bundle of the symmetric product is anti-ample. And then for higher n, it's anti-ample along the fibers. But somehow I have in my mind I'm not completely sure, but I thought I read somewhere in a not so old paper where it's proven only for Pn for n greater equal 3 that then the Hilbert square is.
Yeah, no, exactly.
So
it's
is there some new result, and where is it? Or
yeah, so this Pn result, this is like Sawan, I think. Sawan, is that, I think. We did it for Pn, and then we essentially use this this result for Pn to sort of get it for cubic hypersurfaces as well. And this is in the paper.
Ah, it's okay, great. Okay, thanks.
Other questions?
So can I ask, so I find the integral Chow motives quite interesting that it's true for them. So do we believe that K equivalence implies isomorphism of integral Chow motives?
I don't know. I think there are other people here that probably actually know what to expect there. I don't know. I have no idea what one expects there, to be honest.
Especially the integral ones, because we know that for K3s, derived equivalence implies rational isomorphism, but not integral.
Yeah.
So it's interesting how it mixes in the integral Chow motives.
Yeah, I have no idea what to expect. I would, yeah, I guess John probably has something to say there, but I don't know.
Can I also ask about this chess game? Could it be a step to prove that K equivalence implies D equivalence? So if I wanted to use this statement, is it conceivable to factor K equivalences into elementary steps, which would look a bit like this.
Yeah, but the thing, so this chess game, I mean, it's really very delicate somehow. It's sort of, I mean, it's kind of a big combinatorial thing to do. So it's really, we're sort of lucky that we were able to solve it here. But so I don't know. I mean, maybe, but it seems quite difficult. Oh yeah, I see that you added in chat. So I should add here as well. So apparently this is a conjecture by Galkin. So I think there are also people trying to prove this conjecture by moduli spaces of objects on this Kuznetsov component. But yeah, I would somehow hope that cutting down these SODs is maybe easier. But yeah, I don't know.
Okay, great. If there are any other questions or comments? If not, then, well, thanks again to Theo for the talk. Excellent. Let me stop the recording.